We're joining together for the third and final session here this afternoon on the global climate issue, ecosystem services, and biological sequestration, how those things are interconnected. I think in every single talk you've talked about interconnections, interdependencies, systems perspectives. I think that sort of is a, can you close those doors for us? Thanks. And we really do have a stellar group to help us think this through and to stimulate our thinking. Our overarching speech, our theme presentation is Dr. Phil Duffy, who is president and the executive director of the Woods Hole Research Center. Ecological systems and climate are his area of expertise, and he really has played the role of citizen scientist in many, many ways. Now directing a major research center in Woods Hole, but he also has served in the White House with OSTP and other parts of our government to play the citizen science role. So I think he's really in a great position to help us think through this issue of how ecosystems and climate interact and how they're so much a central part of our future because they do provide the services that provide the life of our planet. Thank you.
Well, thanks very much. I really appreciate the opportunity to talk. I really also appreciate especially all of you sacrificing the opportunity to stand in the hall and drink coffee in order to get a little science lesson. What I want to focus on mainly is the role or the potential role of land ecosystems in mitigation of climate change. And I'm going to make three basic points, and one is that if we want to have any hope of meeting the climate goals that we commonly talk about, limiting global warming to 2 degrees Celsius or even more difficult, 1.5 degrees Celsius, if we want to meet either of those goals, we really need to do massive removal of carbon dioxide from the atmosphere. Limiting future emissions won't be enough. And what I then want to do, after I make that case, I want to show you that the potential for, in fact, removing carbon dioxide from the atmosphere using terrestrial ecosystems that potential is greater than you might think. And finally, I'll just show you some observations showing that healthy forests, among their many benefits, include regulation of local and regional climate in ways that are very, very significant. Okay, so I want to again start by making the case that we need large-scale removal of carbon dioxide from the atmosphere. And to make this case, I'm going to go back to the topic of the previous session, which is the Arctic. And I want to focus specifically on greenhouse gas emissions from Arctic permafrost. This is a picture of some permafrost, ground that's been frozen for probably tens of thousands of years, now beginning to thaw. So what do we think the future greenhouse gas emissions from thawing permafrost are likely to be? This is just illustrating basic carbon budgets, okay? Many of you know that the IPCC says if we want to have a 2/3 probability of limiting global warming to 2 degrees Celsius, that we're allowed to emit a little under 800 billion tons, 800 gigatons of carbon cumulatively over all time. So that's our allowance for carbon emissions from all human sources over all time, okay? You probably also know that there's a growing body of science that suggests that limiting global warming to 2 degrees Celsius isn't good enough, in the sense that at that level of warming there may likely be some very serious irreversible consequences. In particular, for example, it may well be that at less than 2 degrees Celsius of warming, we will have committed to the ultimate melting of the Greenland ice sheet and 20 or 25 feet of sea level rise. So as you know, the Paris Agreement recently concluded talks about the desirability of limiting global warming to 1.5 degrees. If we want to do that, our carbon budget is reduced. It's about 650 gigatons of carbon. And again, that's total human emissions from all sources over all time, okay? So that sounds like a lot, but what this shows is that, in fact, we've already emitted about 550 gigatons of carbon, most of that budget. And in fact, that number may be lower. There was a paper that came out a couple days ago in Nature citing a higher number for emissions to date, 585, okay? But taking this at face value, what this shows is that if we want to meet the 1.5 degree goal, we are allowed an additional 100 gigatons of emissions. If we want to meet the 2 degree goal, we're allowed more, about 240 gigatons of additional emissions, okay? So how much is a gigaton? To put all of that in perspective, at the present rate, we're emitting about 10 gigatons of carbon a year. So that means to meet the 1.5 degree goal, we can emit about 10 additional years worth, not a lot, okay? And the picture gets worse because I haven't factored in yet emissions from permafrost. So what do we think emissions from permafrost will be? This is from a paper in Nature last June showing various estimates of expected future emissions of greenhouse gases from thawing Arctic permafrost. You can see there's a range of estimates, and what I'm highlighting here is the mean estimate for emissions between now and the end of the century, and that estimate is 90 gigatons of carbon. I'm actually not going to use that, though, partly because I want to be very conservative. What I want to assume is, let's assume future emissions from thawing permafrost are only about half that, or only about 50 gigatons, which is equivalent to pretty much the low-end estimate here. But what I want to do is show you what that does to the carbon budgets, and it's not very nice, okay? So if we assume 50 gigatons of emissions from permafrost on top of 550 gigatons already emitted, then we're allowed, if we want to meet the 1.5 degree goal, only 50 gigatons additional emissions of carbon, okay? If we want to meet the 2 degree goal, we're allowed an additional just about 200 gigatons. So my interpretation of and again, so at the present rate of emissions, 50 gigatons is 5 years worth, okay? So my interpretation of this is that unless we engage in, again, massive removal of CO2 from the atmosphere, the 1.5 degree goal is simply out of the question. The 2 degree goal is difficult. So let's look at how this picture changes. What if we could remove 150 gigatons of carbon from the atmosphere? That's a lot, but I'll show you in a moment that that is, I think, the theoretical potential of what could be added to the land biosphere. What if we could do that? And not surprisingly, obviously, just by simple arithmetic, that gives us a lot more room in terms of what we can emit from fossil fuels and still meet these climate goals. So for example, if we could remove 150 gigatons from the atmosphere, that would allow us 20 years worth of emissions and still stay within the 1.5 degree target, 20 years as opposed to only 5 years. So theoretically, it could really help a lot. Okay? So where does this number come from? Where does this number, 150 gigatons of additional carbon storage in the land biosphere, come from? The case for this was made in a peer-reviewed commentary in Nature Climate Change that was published right before COP21. The lead author was Ski Houghton, senior scientist at Woods Hole Research Center, and he walks through the case for that tropical forests in particular could be, at least for several decades, a major sink of carbon, and I want to show you how that looks mathematically. So I'll start with this. This is historical. This you've seen before. This is historical emissions of CO2. The grayish curve is fossil fuel emissions growing rapidly. The greenish curve is emissions from tropical land management, principally deforestation, and this illustrates what you've probably seen, which is that the net emissions from managed lands in the tropics is about now 10 or 15% of the total emissions. The total emissions are shown in black, okay? But what's subtle but very important is that this about 1 gigaton a year of net emissions from tropical forests is in fact a net number, and the gross emissions from deforestation are much bigger, and there's a almost as big sink. And what that means is that by controlling how we manage land in these tropical forests, we could actually reduce global emissions by much more than 1 gigaton and by much more than 10%. Okay, but I'm going to walk you through that right now. Let's suppose that we want to have a 75% chance of meeting the 2-degree goal, okay? And let's suppose that we do that only by reducing emissions of fossil fuels, okay? This dashed line shows what the trajectory for reducing fossil fuel emissions need to be. Very drastic reductions down to 0, okay? Because in order to fully stop climate change, we need to get to net zero emissions, as you all know, okay? But let's suppose now that we not only stop deforestation, but also aggressively reforest areas in the tropics that have already been deforested. And again, this is a theoretical construct, but I'm showing it to you to illustrate the potential. So let's suppose we did that. That allows tropical forests to become a pretty big sink of carbon for a limited period of time, okay? And that's what this looks like, okay? And so this is now the net, well, emissions or sink from managed areas of tropical forests. And as I said, if you assume zero deforestation along with aggressive reforestation, the tropical forest areas can actually become a pretty big sink of carbon for a limited period of time. And the area under here is about a little more than 150 gigatons, which is where I got that number from. And if you want to think of it this way, the horizontal, so this is now the trajectory, the needed trajectory for fossil fuel emissions reductions if we also aggressively reforest the tropics. And the horizontal distance here represents the amount of time that this biospheric sequestration has bought you, the additional time to reduce fossil fuel emissions. And you can see it's 10 or 15 years or something like that. So it's really, it's a lot. Now, I want to emphasize some caveats, and as I've already said, I've made some very idealized assumptions here. I've assumed that there's zero deforestation. I've further assumed aggressive reforestation of areas in the tropics that have already been reforested. As you know, actually doing this, there are massive economic and policy barriers, which basically boil down to trees standing there don't make anybody any money, and other uses of tropical land do make people money. The other thing which you've seen on the previous plot is that the ability of any forest, tropical forest included, to soak up carbon declines over time and eventually stops. And you see that here, okay? So this is, tropical forests are a sink for a while, but after a while they saturate, okay? So ironically, reforestation, right, it's not a sustainable solution to climate change. But my point, and it's not intended to be, but my point is that it could be, the potential for storing carbon in the biosphere is sufficiently large that this should be a tool in the toolkit. Okay, one more point, and that is about the effect of healthy forests on local and regional climate. This is a healthy tropical forest viewed from the air. This used to be a healthy tropical forest. It's not anymore. And this is the boundary between a forest and a deforested region. These pictures were all taken from an area in Mato Grosso, Brazil, where Woods Hole Research Center studies, among other things, the effect of deforestation on regional climate. And what we find is that deforestation has major effects on regional temperature, major effects on precipitation in terms of reducing precipitation, and major effects on what happens to the water that lands on the ground, the precipitation that lands on the ground. Right now in tropical forests, a lot of the precipitation is recycled by the trees back up into the atmosphere, comes back down as precipitation. If you don't have the trees, a much higher proportion of precipitation is lost in the form of runoff. And one of the implications of this, ironically enough, is that deforestation itself threatens the ability to conduct agriculture in these regions, principally because of loss of precipitation. And I say that's ironic because, as you know, the principal driver, in fact, of deforestation is actually agriculture. So let me just illustrate this quickly. Here's a couple satellite views. This is, on the left, patterns of land use from, I think this is from MODIS. On the right, same region, surface temperature. You can see clear relationship. The forest-covered areas are much cooler, and we observe that universally. This is showing what happened to a region, and I'm not sure exactly where this is, but a region that was originally forest until about 2006, and then it was cleared and turned into pasturing land. And this shows the effects of that land use change on evapotranspiration, sucking of moisture out of the surface back into the atmosphere, net energy exchange, and also temperature. So this change in land use pattern has had major effects on the climate of the region. Okay, so before I close, I want to just give one parting shot, which is slightly off topic, but that has to do with the issue of forest biofuels. There are some unfortunate policies in place and under consideration which would legislate that forest biofuels are carbon neutral. They're not, even in very idealized conditions, they're not. This is from a recent paper that was published this year showing, for those of you who know it, it's the global warming potential, 100-year global warming potential of forest biofuels. For those of you who don't know what that term means, it's essentially an averaged measure of the climate impact of forest biofuels compared to that of CO2. And so it's a dimensionless number somewhere between 0 and 1. You can see there's a lot of regional variation. The average is about half, which is saying that forest biofuels, in terms of their 100-year climate impact, are about half as much as CO2, which may be okay. Well, it's better than CO2, better than emitting CO2, but it's not good enough. Okay, so I want to leave you with this, and this is from a paper that was published 3 days ago. I really encourage you to read it. It's about the deep time implications of climate change, the 10,000-year plus implications of climate change. Policy decisions made in the next few years to decades will have profound impacts on global climate, ecosystems, and human societies, not just for this century, but for the next 10 millennia and beyond. I think it's really profound and really important. Thank you.